Hello, everyone, and thank you for joining us today. My name is Andrew Moore, Marketing Manager with ASCE Publications and Standards. Before we get started, a quick housekeeping note. Today's session is being recorded, and the recording will be available after the event on LinkedIn and YouTube. We will not be distributing the presentation slides. Today's session focuses on snow load provisions in ASCE 722, specifically what changed and how to interpret those changes correctly in practice. ASCE 722 introduces important updates to how snow loads are defined and calibrated as part of a shift towards consistent reliability-based design. Understanding that context is key to using the provisions correctly. This session is not a walkthrough of calculations. Instead, it focuses on intent, context, and correct interpretation, which are critical for consistent application of the standard across projects and jurisdictions. We're very pleased to be joined by Jeannette Torrents, Technical Director of ASCE's Structural Engineering Institute. Before joining F.SEI in 2025, Jeannette spent more than 20 years as a practicing structural engineer, applying ASCE 7 snow load provisions on projects across Colorado. She also served as chair of the Structural Engineering Association of Colorado's Snow Load Committee for nearly 2 decades. That combination of long-term experience and leadership in snow load guidance gives her a clear, practical perspective on the ASCE 722 updates. Today, Jeannette will walk through the updated snow load provisions, discuss changes to the snow load factor and load combinations, and help clarify how to make meaningful comparisons between ASCE 716 and ASCE 722. Please feel free to submit questions in the comments as we go, and we'll address them near the end of the session. Jeannette, with that, I'll turn it over to you.
Thank you, Andrew. So, as Andrew said, we're going to go through what changed with ASCE 722 snow loads, and most importantly, what it means in practice. Quick note before we get too far in, as Andrew said, we will be sharing the recording of this presentation. We do ask that you don't feed it into any AI systems without written authorization from ASCE. Okay, so there are 3 main updates in ASCE 722 with regards to snow loads. And those are reliability targeted ground snow loads, updated thermal factors, and a new winter windiness factor and updated drift equations. Today, our presentation is just going to focus on the largest change, which is the reliability targeted ground snow loads. So let's start by talking about ground snow loads and why we're moving from a nominal ground snow load to a strength level ground snow load for design. So I hope that most of you are familiar with the ASCE hazard tool. This is a free tool online at ascehazardtool.org, and you can use it to pull up hazards from different versions of ASCE 7 for locations across the country. So what I have shown here is ASCE headquarters, and I've chosen ASCE 716 and risk category 2. And I think that this is, for most people, their initial introduction into what's different with the snow loads. So if I choose different values in my drop-down menu, and I instead select 722 snow loads, we initially have a significant difference. And I think this alarms a lot of people. What's important to remember when we look at this difference is that the load combinations in ASCE 722 for snow have changed versus ASCE 716. I'm just showing the load combinations here where snow is the controlling or primary load in the combination, but all of the snow-related load combinations have changed. So you'll see in 722, there's actually a factor of 0.7 on snow for allowable stress design, whereas there was no factor in 716. And for strength design or LRFD design, the load factor is now 1.0 and not 1.6. Another important thing to point out is that the ratio of the ASD to LRFD loads have changed between 722 and 716. If we look at the ASD LRFD ratio of 722, it's 0.7. And 716, it was 0.625. And this change in ratio in the load combinations is important because what was determined was that for the ratio of snow loads in 716, you weren't getting consistent reliability between ASD and LRFD. And the idea is that regardless of which method you use for design when following the ASCE standards, you should have a same safety or reliability or protection against failure for your structure. So that ratio corrects it in 722, that change in ratio, and we've gone to strength level design just like ASCE 7 previously did for wind. So when we look at that and we say, okay, let's compare our ASCE 722 load and factor up our ASCE 716 load by 1.6 so that we're comparing apples to apples, that's better, but there is still an increase. So now we're looking at 69 versus 40 instead of 69 20 versus 25. So why is that? Well, the big advancement in 722 is that we've gone to reliability targeted loads. Why do we need to update the ground snow loads? So if we look at the map from 716, you'll see that the last significant update in the methodology behind the ground snow loads is from 795. So that's several years ago, not just in terms of advancement and understanding of reliability and technology, it's also 30 more years of data to be looking at when we're looking at loads. The 716 map had significant case study regions, which are these regions shaded in light blue here. We had big steps across state lines where every state had some of the case study states had their own special map and region and tabulated values with inconsistent methodology across state lines. And most importantly, it was determined that the 50-year ground snow loads that were the basis of design for 716 resulted in non-uniform reliability across the country. So you could design a structure in one state and another state to code with the exact same demand capacity ratio given by the standard, and you would have a higher probability of failure in one state than another state because of this non-uniform reliability. So let's talk about what 716 was based on. So what 716 was based on and what was mapped were 50-year ground snow loads. So as a refresher, a 50-year snow load means that that has a 2% annual probability of exceedance. So every year we have a 1 in 50 chance of seeing that load. Over a 50-year structure life, that means that a building has a 64% chance of seeing its 50-year snow load at least once during its structure life. We don't need to worry about 64% of the building seeing that snow load because when we design, we're not designing directly for that snow load. What we're doing is taking the nominal load, and in stress design, we have our demand on one side, which for 716 was our 50-year load, and we're dividing our capacity on the other side by a safety factor. With strength design, we put a load factor on the demand where we increase the load, and then we reduce the capacity by a resistance factor. And so what that means is that even though we're expecting 64% of these structures to see their 50-year load within their lifetime, they're all sufficiently designed, at least in theory. So when we're talking about sufficiently designed, we need to talk about reliability targets. And these are in Chapter 1 of ASCE 7, and they're used to calibrate the hazards across the standard. And what we do is we're looking at beta, which is a reliability index, and that corresponds to the probability of failure of a structure. And the probability of failure that we're going to allow is higher in risk category 1 structures than it is in risk category 4 structures, which means that the reliability index in a risk category 4 structure is higher than the reliability index of a risk category 1 structure. And this is how we balance safety versus cost. So when we're looking at our targets, we have individual targets for each structure type. However, when you do a reliability analysis on taking a 50-year snow load and either factoring it up by that load factor that we talked about for strength design, or comparing it to the capacity divided by a safety factor for allowable stress design, we find that this load doesn't consistently hit ASCE 7 reliability targets. We find that in some places, like the mountains of Colorado, we see risk category 2 structures complying with the reliability targets for hospitals, which is not an economically feasible solution. And then we see in some other locations, we have structures across all risk categories only hitting that reliability target for risk category 1 structures, which represent a low hazard to human life. So this is a problem. We're not consistently balancing safety and economy to the levels that we are doing for all other hazards, and we're seeing variation across the country and across climate zones. So the way we need to look at this and the way that we determine our reliability indices is we have to take a look at the distribution of our demand and our capacity. As we know, snow is variable. We see a lot of variability from one year to another. Capacity of structures is also variable. If you think about the example of, say, a steel beam, you're going to have not every steel beam, when we design it to be a 50 KSI yield strength, is actually going to have a 50 KSI yield strength. Most of the sample specimens you take are going to have a higher yield strength. There's also variability in the section properties of the manufactured shape and what that looks like. And that all results in a probability distribution function for capacity. So in this chart, we have our blue, which is representing our demand, in this case, snow. And we have our green, which is representing, in this case, the capacity of our structure. And when our demand is less than our capacity, we're fine. The structure passes. Our reliability target is set for an appropriate intersection of what we're going to allow those two curves, how much we're going to allow them to overlap. Because we're not saying that we're going to design for structures to never fail. We're just going to say that the probability of failure has to be sufficiently low so that it meets the reliability target for the risk category. And so you can see here that when we have a snow load that is higher and is in that overlapping zone and is starting to overlap with the capacity curve, that doesn't necessarily mean that the structure is going to fail when we have that higher snow load, because the capacity of the structure might be higher than what we targeted the design capacity to be, just like we talked about with some of the overstrength that we find in materials or redundancy in structural systems or those sorts of things. So in this case, it still passes. However, you could have an instance where you have your structure that is designed for an acceptable target level in the code, and it's now lower than the demand that it experiences. And when that happens, we have a failure. So what we do when we're doing a reliability analysis is we do a Monte Carlo simulation. So we pick a sample structure. In the case of snow loads, it's a very simple flat roof building with a 30-foot span, which is a wide flange steel beam, 30-foot trib width, a relatively low dead load of 15 PSF, so that snow should control the design. And we design it for the flat roof snow load given an ASCE 7 of 0.7 times the ground snow load. When we do that, basically run 1 million simulations for every computation. So what that is it's taking random points anywhere around along that curve. So picking a spot on the blue curve and a spot on the green curve. The likelihood of picking that spot has to do with the intensity. So those peaks that we saw, which were the typical values, those are more likely to pop up. And the ones on either end, which we would call the tails, are less likely to pop up. And each simulation generates a random demand and a random capacity. And you're looking to see how many times we get a pass with the green check mark, and how many times we get a fail with the red check mark. Now note that there are different variables that go into each of those curves. We already talked about some of the random variables that could be in a capacity curve. We also have random variables in the demand curve, and that is both in the ground snow load and also in how much of that ground snow load actually is reflected on the roof. We use 0.7 for design. Again, this 0.7 is not the 0.7 from the load combinations. This is just a ground to roof conversion factor that's in the code, but that has its own variability to it as well. And then we run that a million times, and then we see, well, what is the percentage of failure that we got from that simulation, and does that give us a reliability index or not? And if it didn't, we need to increase the snow load we're using for design. And if it was much higher than we need it to be, then we can back off on the snow load used for design. So how is this done? So this is a nationwide effort to come up with the new ground snow loads. So these are all the data points that were used. So you can see there are more than 500,000 annual snow load maximums and more than 12,000 stations across the country and a little bit into the border with Canada. These are from NOAA data sets, National Weather Service, anywhere that has record of snow weight or snow depth where we have to convert it to an equivalent weight. As you can imagine, with the Monte Carlo simulation that I described, this was a significant effort, and so I want to take a moment to acknowledge the financial support that made this possible for this research project in order to inform the provisions in ASCE 7. Okay, so when we have our data points, what do we do with those? The first thing is to fit a distribution to the data. So how that's done is you take all of the data points and you graph a histogram, which is showing your number of observations within a given range. The density is the relative frequency of occurrence. So in this particular histogram of snow loads for Rochester, New York, you'll see that most of the time, the snow load is somewhere between 10 and 15 PSF. That's where the peak is in the distribution curve. But they do have some snow loads on record that are up past 40 pounds per square foot. And it's really those outliers, or what we call values that are in the tail of the distribution, that we want to be careful to account for when we are trying to prevent failure of structures under extreme events. So to illustrate that a little bit more, I'm going to show this slide that shows you the histograms or probability distribution functions for snow in 3 cities with very different climates. So we have Minneapolis, Minnesota, where you can see that this is a more normal distribution. You don't see a lot of outliers here, and this is fairly typical in areas where the design snow load is a function of several storms accumulating over the winter. And during the winter months, the temperatures are often below freezing, which means that precipitation is going to fall as snow instead of rain. In a place like Boston, Massachusetts, you can see that the distribution starts to be a little bit skinnier and have a little bit of a longer tail. And then a place like Baltimore, you can see that it has a very long tail and it's a very skinny distribution, I would say. So most of the time in Baltimore, you're having snow loads that are quite low, but they do have some observed conditions that are higher. And that's because Baltimore gets a lot more precipitation in the winter than Minneapolis. It's just most of it typically falls as rain instead of snow, but it's right on that average temperature where if you have an unusually cold winter and you get a big storm, you could have a very heavy snow. And this is a typical profile for places that are governed more by a single storm event and not the accumulation of several storms over the winter. So if we look at these graphs, we have on here our black dotted line, which is our strength level load under 716, so 1.6 times 716. Ground snow loads, or 1.6 times our 50-year snow loads. And then our red is our 722 strength level snow loads. So you can see that in places like Minneapolis, where the distribution is much more normalized, we can actually come down on the required snow loads because we know there's just not as much variability we need to account for. A place like Boston, the current code provisions fit the reliability targets and they're achieving them. So there's not much change. But in a place like Baltimore, where you have that variability with both temperature in the winter months and precipitation, the load needs to increase in order to hit the reliability targets. And so what that means is you can have 3 places with very different climates and very different profiles end up being designed for similar snow loads. So when we look at what that looks like when we take those 3 different shape patterns and we expand them across the country, we get a map that looks like this. So if we look at our purple, that's more of a Baltimore shape distribution. It has what we call the heavy tail. And as you can see, it's places that get snow and have precipitation, but it can be variable. And then you can have the orange is more normal distribution. And these are the places where you're typically going to have snow in the winter. You're typically going to have accumulation over several storms, and it's typically going to be pretty cold in the winter months. So how do we fit the models? So this is one important benefit of doing a nationwide study, is we can fit them by ecoregions instead of looking at them by state. So ecoregions are regions where geology, landforms, climate, and hydrology are similar. And so we don't have to respect those geopolitical boundaries. We can really look at the climate boundaries when we're looking at the different models and distributions. Okay, so now we'll talk about how all of that research translated into maps in 722. So this is the final map. What I want to point out with this map is the gray areas in 22 are not case study areas. These are areas where the ground snow loads exceed 140 PSF, and you're referenced to the geodatabase, which is available in the ASCE hazard tool, in order to see what the values are in those areas. And these areas with very heavy snow loads also have very tight contours. What this results in is reduced case study areas, 91% fewer case study regions. And most of these case study areas are areas where the elevation or some other factor exceeded any value that was in the data set that we had for analysis. So it's not something that we could determine and take a look at. Most of these locations are above the tree line, and there probably aren't a lot of structures there, but it is something to consider. Okay, so when we're looking at what the actual values look like, this is a map that just represents where we have heavier snow loads and where we have lighter snow loads across the country. And to help people translate this to the snow loads that they're used to, this map has taken the 722 loads and they factored them down by 1.6 to be able to compare back to what the old PG would have been. And so you can see that in the mountains, we have some loads that are above 120 pounds per square foot. And then we have other areas where the load is 0. But I want you to look carefully at the title of this map, which is the risk category 2 map. If we look at the reliability targets that we were talking about before, where we have a different reliability index we're trying to hit for essential facilities, risk category 4, and we compare that to risk category 2, you will see that in order to hit the reliability targets, we have a lot of different colors on this map. In areas such in Florida, where we typically don't design for snow under risk category 2, we do have to design for and think about in an extreme event, and a facility that has to stay open, like a fire station or a hospital, has a pretty high ratio of the 4 to 2 loads. That also tends to happen where the 2 loads are very, very low. So what does this mean? It means that we can't anymore use a consistent load factor or an importance factor to adjust from one risk category load to another. So in the previous code, risk category 4 versus risk category 2 was a ratio of 1.2. That was the risk category 4 snow load importance factor. That were appropriate to hit reliability targets, the entire country would need to be this light purple, and that's not what we're seeing. So what that means is no more importance factor, and much like wind, it means that we've now gone to 4 different maps. There is a separate map for every risk category. Okay, so let's talk about what those look like a little bit in practice and how minimum roof loads have changed and how to think about serviceability in conjunction with this. So here's the new table for minimum snow loads for low slope roofs. Since we no longer have an importance factor, we now have to provide one for every risk category. And remember that the snow loads are now strength level loads that are factored down by 0.7 for use with ASD or are used directly with strength level design. So that's why these numbers are different than you're used to, but the actual minimums when you're doing an apples to apples comparison for risk category 2 are equivalent to what you had before. In the 2024 IBC, which adopts the ASCE 722 snow loads, in the serviceability table, there is a footnote that specifically says that you can take the snow load as 0.7 times the design snow load in order to determine deflection limits. And what that is doing is it's taking it from a strength level value down to an allowable stress value. That being said, as we talked about before, that allowable stress level value no longer relates to a set mean recurrence interval. It's no longer a 50-year snow load. In some places, it represents a load less than 50 years. In other places, it's a load that's higher than 50 years. So ASCE 7 does have some recommendations in the appendix that suggests using a 20-year MRI ground snow load when you're doing serviceability checks, and that would be a snow load with a 5% annual probability of exceedance. So that can help you exercise your engineering judgment when you're trying to make a decision about appropriate serviceability levels to hit your design targets. So how do you find these? If you click on the details button in the hazard tool, you'll see that the 20-year MRI value is provided. Again, this is in the appendix. This is not a mandatory value. It's just provided for reference and can help you understand the very realistic load that the building is quite likely to experience under its design lifetime. I also want to point out something that's at the bottom of the ground snow load table. So I think, as we all know, the IRC is a prescriptive code. It's based on tables, and it was not ready to convert using a strength level design value. So there is this PG ASD term that is a term that only exists in the IRC, and that is provided here for your convenience. All this is doing is it's taking that 0.7 load factor in the ASD load combination and applying it to PG. So it will always be 0.7 times PG. What I have heard some people getting confused about is they think, oh, this is my PG ASD that I'm then going to use with my IBC load combinations, or I'm going to use it with ASCE 7. And that's not correct. That would be double dipping. I want to emphasize that the PG ASD is for IRC only. Okay, so we should talk about cost impacts. What does this really mean for structures? So Nucor Building Systems and Volcraft did a cost analysis, and they found that there's an increase in demand, an increase in the weight of the roof structure, resulting into a 1 to 2% average increase in the weight of the total structure. So you can see this box plot over on the side. That is the roof joist total loads, so dead plus snow, 722 compared to 716. And you can see the X in the box plot as the average, which is the 5% increase. But what does that mean when we go outside to the extremes of the box plot and we're somewhere up here like we would be in Baltimore, where we have a 30% increase? So again, how did we get there? We have our old snow load. We put it in our old strength level combination. This was with a dead load of 20 pounds per square foot. Make it a 64 pounds per square foot demand on the roof. even though the ground snow load under 22 is 60, our total load is the ratio of our dead and our snow. We put it in our new strength level load combination, we get 84, or a 31% increase in roof demand. They looked at metal building structures with different aspect ratios and different roof slopes, and they found these weight increases for the metal building and these cost increases for the metal building. But when they looked at the total cost impact, when they were looking at foundations and all the different pieces of the building, they found it was still only a 0.8% to a 0.9% cost increase. Obviously, this is going to vary depending on where you are, your building parameters, your site, all of those things. But at least for this particular scenario, the large increase in snow loads did not have a significant impact on cost. Okay, so in summary, the new ground snow loads incorporate 30 more years of data. They provide consistent reliability across the country, and they avoid conflicts across state lines. Important things to remember that I see people forgetting all the time is there is no more importance factor, there are new load combinations, and you need to use the ASCE hazard tool to get your values. Want to mention one more time that there are other updates in ASCE 7 snow loads that you should be aware of, such as the thermal factor and winter windiness and drifts. And we do have resources available for you in ASCE. If you have a subscription to the ASCE Amplify platform, you can see the standard and commentary side by side. You can also look at the versioning history, so you can look at 7.16 versus 7.22 side by side. There's this design guide for snow loads that steps through examples of stepped roofs, drifts. It talks about some of the background that we just covered today. And then we do have more in-depth on-demand webinars available that are more technical and not as high level as today's presentation. If you're searching for them in the ASCE catalog, these are the titles. So with that, I'm going to turn it back over to Andrew and see what questions came up. Yeah.
Yes, thank you. That was fantastic. And so we do have a few questions so far. So we actually have one from Timothy. Since the modeling is based off of steel beam, would using a wood beam create a different snow load map?
So this is why ASCE 7 is gone to strength design and using that as calibration for everything. Because what strength design does is it decouples your load and your capacity, whereas allowable stress design puts both of the variabilities into a single safety factor, which, as you pointed out, can vary a lot with wood. So the strength design would be the more accurate way to go, and then we can have consistent load maps across the country. And we're just dealing with the variability in wood. And as you know, whether you're in compression or tension, you have to use different fee factors and what all of that looks like. You just handle the material that way.
Okay. And we had someone ask about differences in the hazard map tool in different areas. And if they had questions like this, would the peer-to-peer standards exchange be a good forum for that?
You can put that in the peer-to-peer standards exchange. There's also, if you go to the hazard tool, there's a question mark button. So if you are seeing values that are different than the print map, we should talk about that. I will say the way the hazard tool works is it has a gridded data set across the whole country, and those grid points are half a mile apart. So if you happen to see a spot that, especially if you have areas of a lot of variation in elevation, you want to check your mapped elevation versus your actual elevation, because it could be pulling from the closest grid point, which has a different elevation than what you're interested in. So you can pick the Find on Map button and pick a value a little bit over, and then you'll get something closer. What I will see with those variations that you were talking about, while we are mapping and doing our interpolations to the best of our abilities, we don't have data everywhere, right? We tend to have data most at weather service stations that are at places like airports. We also have a lot of data in the mountains where people are monitoring snowpack to be able to predict runoff for the spring and how much water we're going to have. So there are some variabilities. If you're within a certain ratio or even 5 pounds per square foot, I really don't think that we're able to say for certainty that we know snow to the nearest flake, which is also why I encourage people when they're doing their drift calculations, etc. Don't say that your drift is 5 foot 7.5 inches long. And it's 37.8 psf. We can calculate those numbers, but they don't truly have meaning.
Okay. We had someone ask where they can find the recording after. It will be available on this very post on LinkedIn, on the ASCE Publications LinkedIn page, and also the F.SEI YouTube channel.
Yes.
And then we had someone else. So Ted asked, did the cost analysis consider the increase in seismic weight causing an increase in the lateral system? Baltimore doesn't have a very high seismic demand, so maybe it doesn't matter there, but it does in Southern California.
That's a good question. I will say that the cost analysis did not look at increase in seismic weight. There are changes in the seismic chapters when you're in 722 that talk about the percentage of snow load that you need to use as part of the seismic weight. And those are calibrated to work with the adjustment to go from allowable stress to strength design. That part has apples to apples tracking. But if you have, even after you've done the apples to apples comparison, an increase because of the additional years of data or needed to increase to hit the reliability targets, there will be an increase there. And I am not aware of any studies that have looked at cost impact for that.
Okay. And then we have, does the cost analysis include both greenfield and brownfield construction?
I don't believe so. We'd have to ask Newcourt and Volcraft, but I think it was really just looking at greenfield construction, brand new construction.
Okay. And then can we use the ecoregions you mentioned to help make a more accurate conversion from 716 snow to 722 snow? The general 1.6 factors seem to fall short at times.
Well, the problem is the 1.6 factor going from 716 to 722 is just comparing what was required for strength level design in 716 versus strength level design in 722. The 16 values have no relationship to ecoregion, and they also have very inconsistent reliability targets. So, they have the same targets, but they weren't hitting them. They have inconsistent reliability indices. So it's really just taking a look at what are the impacts on your design. You cannot take the 716 snow load, factor it up by 1.6 and say you're going to use it as a 722 snow load. That's not appropriate. If you don't want to use the 722 snow loads, you need to do a reliability-based study that is a case study specific study to your area that does those Monte Carlo simulations and all the things that we talked about in order to find what's equivalent. So for example, Colorado has done that. And so they were able to get more granular with things than that grid that we were talking about before. But what they are not is taking 50-year snow loads and factoring them up.
And then one last question. How is climate change considered in these changes?
That's a great question. Climate change is not considered in ASCE 722, but we are looking at incorporating climate change into 728. We're currently balloting a new chapter called Future Conditions, and it's looking at variability. And so in most places, when you're looking at how the snow load impacts will be, we're seeing a factor of 1, where we're not going to say that there's an increase because the winters are getting warmer, maybe we're having less snow in some areas. In other areas, what is happening is we're having greater variability and instability, and we do have some higher values. For example, you may be familiar with recently there are some significant roof collapses in Anchorage, Alaska, which is traditionally a place that receives snow and understands snow. But with the winters being wetter and warmer, the density of that snow is different, and it's not what was expected. So I say stay tuned for 728 and some updates there.
Okay, and we'll wrap up the Q&A right now. Thank you, Jeannette, for a clear and thoughtful discussion. And thank you to everyone who joined us today and for the great questions in the chat. As a reminder, today's recording will be available on the ASCE Publications LinkedIn page and on the F.SEI YouTube channel. For official ASCE 722 resources, including the standard training and updates, you can visit asce.org/ASCE7. We appreciate you spending time today with us, and we look forward to continuing the conversation in future ASCE Publications live streams. Thank you and have a great rest of your day.